Okay, the last lecture. Let's recall what we did last time. We discussed zero divisors. So it's a question about groups. Zero divisor conjecture. Given a group gamma, and let's assume it's torsion free. Is it true that, so the conjecture states that it is true that for any alpha and beta in a group ring, and we are free to pick, for example, coefficients, any field. So I will be working with complex numbers. Say, let's take complex numbers. The group ring with complex numbers as coefficients. For any two numbers which are non-zero, we have the product of these numbers is also non-zero. You remember that we restated this question equivalently in a slightly different form. We considered, so pick some beta in a group ring which is non-zero, and consider the map. The map of multiplication on the right side by beta. L2 C of gamma to C of gamma. This statement is equivalent to saying that if something goes to zero here under this map, then that something should be zero. And that's equivalent to saying that this map is injective. So the zero divisor conjecture is equivalent to saying that for any such B, the multiplication by B is injective. That's obviously clearly an equivalent restatement, but now this way of thinking of the problem allows generalizing the statement, making it more stronger. So consider L2 of gamma instead of the group ring. The group ring consists of all finite linear combinations of elements. L2 of gamma you can think of being, the way I define it, it was functions from gamma to complex numbers. But any linear combination can be thought of as a function. So if you have alpha sub g, then equivalently you can think of this being a function that assigns to each element g assigns alpha sub g. This is a function from the group to the complex numbers. So any linear combination like this can be thought of as a function of this type, such that only for finitely many g's we have non-zero values. So most of the values are zeros, but except for finitely many. And then we can replace C gamma with L2 of gamma, because we are just replacing finitely supported functions by functions which are not necessarily finitely supported, but which are required to be L2 summable. So the same L2 of gamma to L2 of gamma. And this map is given by multiplication by beta. So you have a function in here. Again, or equivalently, given any function, I can think of this being an infinite linear combination with the property that the coefficients sum up. The L2 norm of that linear combination is finite. And that's thinking of linear combination, you define what multiplication means. It should be clear that this is well defined. Even though this is an infinite linear combination, if you multiply it by beta, you will again get an infinite linear combination, but one needs to check that you still have an L2 summable linear combination. And that's a little exercise to check. You just use the fact that beta has finite support. So beta is a finite linear combination of those delta functions. Remember, delta sub x, where x is in gamma. The beta can be thought of as a finite linear combination of such. And for beta sub x, it's pretty clear. Then the map induced by multiplication with beta sub x is indeed takes place, the images take place in L2 of gamma. You just translate the basis by x. The next step of generalization, now when you wrote it in this form, now you see immediately that why should we consider just one copy of L2 of gamma? We can take several copies of L2. So pick some m and n two numbers, and you can consider the map L2 of gamma to the power m to the L2 of gamma to the power n for two different numbers. But now, what would be the analog of this map? Instead of just multiplying by one element of the group ring, we actually should have a matrix m by n, whose entries are just like this beta. The entries should be in a group ring. So consider the following map times m, given by a matrix m by n with entries in the group ring. This brings us to the statement of the Atiyah problem. Atiyah stated somewhere in the 70s or 80s that he introduced the notion of L2 beta numbers. It was due to Atiyah. He did it analytically in a case of manifolds. There is an analytic way of defining L2 beta numbers. This is similar to if we restate it in our terms. So you start with some manifold, say x, and there is a way to define. There is an analytic way introduced by Atiyah to define L2 beta numbers. This corresponds to taking, say, the universal covering of x and considering the group action on that universal covering, and taking the definition that we used for the group action. So what's the conjecture? It's called sometimes it's called a conjecture. It should be called the Atiyah problem rather than the conjecture. In his paper, he asked a question. After introducing those numbers, his question was, when can it happen that those numbers can be not integers, or perhaps irrational? So there are, when you talk about the Atiyah problem, there are several versions of it. First of all, one can consider different coefficients in a statement. Let's work with complex numbers all the time. And second, one can consider the rational version of it or the integral version of it. So the integral version of the Atiyah problem says the following: if M is a matrix as before, so as above, then I should assume, since I'm talking about the integral version, and I need to assume that gamma is torsion free. Torsion free, then you consider the operator of multiplication on the right by this matrix. Since it's multiplication on the right, we have a group action on this and group action on this. So these are gamma modules, but those are left gamma modules. The group action is on the left. Since the multiplication is on the right by this matrix, the group action and multiplication by the matrix, they commute. We can apply the matrix first and then some group element, or vice versa. First some group element and then the matrix. We'll get the same result because of the difference between left and right multiplication. They commute. They are independent. If gamma is torsion free, then one can consider the kernel of this map. The kernel of this map is invariant under the group. And the reason being is that the image of the kernel, by the definition, the kernel is the pre-image of 0, but 0 is invariant under the group. And since the map commutes with the group action, it means that the kernel of this map also is invariant under the group. Since the kernel, so the kernel would be a subspace in here, and more precisely it will be a Hilbert submodule of this Hilbert module, Hilbert gamma module. So one can talk about the dimension. And the statement says that the dimension over gamma of the kernel of that map, of the multiplication by a map, is an integer number. You remember the definition of gamma certainly does not imply that the dimension always should be integral. And it's a homework exercise to actually produce an example when it's not. Those L2 beta numbers. I mean, we talked about L2 beta numbers, but this question is related to L2 beta numbers. For example, if you always have this for any group, then if you consider the group action on some complex, so assuming the conjecture is true, then, yeah, I should call it a problem. Assuming the idea problem is true, then if you have a group action on some complex, then the Betti numbers of x hat, again, I'm assuming free action and co-compact, there should be integers. So, assuming the problem, this follows. Why does it follow? Because the L2 Betti number is the quotient of the kernel. It's the I-dimensional homology to the I-1 dimensional homology. And the previous map is C. So this is di plus 1. What is this? You take the kernel of this map and you divide by the closure of the image of this map. But what is this map? The boundary map, one can check, it's just immediate from definition, that this boundary map commutes with the group action. And since it commutes with the group action, it suffices to define it only on the basis of this Hilbert space. If we know it on a basis, then we know we can extend by linearity to the whole space. But defining it on the basis is equivalent to picking a matrix like this. Once you know it for the choice of basis is those are exactly the entries of that matrix. So it's immediate that the boundary map is given by some matrix. Say di, some matrix m sub I. As before, so it's a matrix m by n for some m and n, and the entries are in the group ring. Yeah.
By the way, do we mean B or beta?
Oh, I wrote beta here. Sorry. Yeah. Sorry. Yeah. That also used. So. The L2 Betti number. So if we assume the conjecture, the Atiyah problem, then this boundary map is given by some matrix, but this boundary map is also given by some matrix. So what is this Betti number? It's the kernel. You take the kernel. What can we say about the dimension of the kernel? It is integral if we assume the problem. Then what can we say about the dimension of the image? You take the image and then closure. What's the dimension of the image? The dimension of the image is you use additivity of dimension. It's the dimension of this space minus the dimension of the kernel. But the dimension of this space is an integer. This is just several copies of L2 of gamma. Each L2 of gamma has dimension 1. So L2, the dimension, as I wrote before, L2 of gamma to the power m is m. And this is of that type. It is several copies of L2 of gamma. So it's an integer. And the kernel, if we assume the problem, the kernel is also an integer. So the difference of two integers is again an integer. The image of this map has integral dimension. So the kernel has integral dimension, the image has integral dimension, the closure of the image. And then we take the difference of the two. This is exactly, the homology is the quotient of the kernel by the closure of the image. So this number is a difference of two integers, so it is an integer. Assuming that problem, this follows. And actually, conversely, the converse is also true. If it's true that, given a group, if it's true that for any action on complexes, all the L2-bit numbers are always integral, then that statement of the ITA problem also holds. So this is a statement in terms of the kernels. You remember, it kind of corresponds to that A submultiplicativity I talked about. It's the dimension of the kernel, and this corresponds to the B version of it, right? When you talk about the L2-bit numbers, but they happen to be equivalent. If you know that for all possible actions of a group, L2-bit numbers are always integers, then this ITA problem is true in this formulation. So two different versions. How does this relate to the zero divisor conjecture? It turns out that the ITA problem, so AP, the ITA problem implies the zero divisor conjecture for gamma. So the ITA problem for gamma, maybe I should say for some group gamma, implies the zero divisor conjecture for gamma. So assume the ITA problem, and you actually need only the case when m and n are 1. So consider this map. So take this beta in C gamma minus 0. Consider the corresponding map C gamma to C gamma, multiplication by beta. Then extend this to L2 of gamma, again multiplication by beta on the right, L2 of gamma. All we need to check is that this map is injective. We will show it by proving first that this map is injective. So if this is injective, then this is as well, because this is just an extension of it. Why is this map injective? So we assume that the dimension of the kernel of that map is integral. But what's the dimension? So again, dimension of gamma of L2 of gamma over gamma is just 1. And the kernel is part of this. So if it's integral, there are only two choices. Either the kernel is 0, either the dimension of the kernel is 0, or the dimension of the kernel is 1. So if, let's consider the case, if the dimension of the kernel of this map is 1. If the dimension is 1, it means that, so what does it tell us? It means that the kernel must coincide with the whole space. Kernel is closed by definition. So we have a space of dimension 1, and we have a closed subspace in it, which also has dimension 1. Then you can use additivity, right? You can write a short exact sequence. You start with the kernel, then this term, and then the quotient. If the quotient is non-zero, then it will have positive dimension. And that would imply that these cannot be the same. So I'm just using additivity. From the fact that this is 1 and this is 1, it immediately follows that kernel of beta is just the whole thing, is L2 of gamma. Because it is closed. More generally, it would be you would need to take closure, but we need to be careful. If we want to talk about Hilbert spaces all the time, we should take closures at appropriate moments to make sure that we talk about Hilbert spaces. Hilbert spaces should be complete by definition. So if you have a subspace in a Hilbert space, you make it complete by taking the closure of the subspace. If the kernel of this map is the whole L2 of gamma, what does it tell you? I claim that this is impossible. Why not? Because in this space we have a very particular element, namely the identity of the group. So it's the delta function which is given by the identity element of the group, whereas 1 is the identity of gamma. And if you multiply this identity function by beta, so beta 1 times beta, that's beta. You run the definition of multiplication, how we multiply linear combinations, right? It's just 1 multiplied by a linear combination of some elements. You will get the same linear combination. But beta is not 0. So therefore, this delta 1 does not lie in the kernel. That means that this cannot hold. This gives a contradiction. So this is false. And the only case left is then the kernel, the dimension of the kernel, dimension gamma of the kernel of multiplication must be, the only option left is that it must be 0. But then, by the homework exercise, it implies that the kernel is 0 as a space. The kernel of this map, this is a Hilbert subspace, and this by itself is the 0 space. And that implies that multiplication by beta is injective. It's injective in this sense, and therefore it's injective in this restricted version. So injectivity means that 0 divisors hold. Conjecture for gamma holds. Okay, so it's an interesting question then. If you're interested in 0 divisors, you might be also interested in the Atiyah problem. Under what conditions does that hold? And I also, let me mention, there is a rational version of this problem, right? It kind of comes from the same question by Atiyah. He was asking, can it be rational, or can it be non-integer, or can it be irrational? But the rational version, what I stated there was the integral version of the Atiyah problem. The rational version says that given any group with no restriction, for any group gamma, the dimension over gamma of the kernel of the matrix as before must be a rational number. So we do not assume, you remember in the integral version we assume that the group was torsion free. Here we just take any group. And this rational version is known to be false. So there is a paper due to Austin that shows that there are matrices. There are matrices M like this, such that the dimension of the kernel multiplication by M is irrational. And even transcendental, if you like, you can make it. So very many, and there are many of them. And the argument was by some kind of probabilistic methods. There are many examples of groups, and they all should have different dimensions of the kernels. But there are very many, uncountably many. That shows that some of them must be irrational. How can one try to prove this? Try to give some examples, for example, for the ITA problem, or to try to prove it in general. There is also a partial result due to Linnell. It says the following, that the ITA problem is true if so he did it for 3 groups, but actually if you read the argument uses the fact that 3 groups are left orderable, and you don't really need to work with 3 groups. You work with left orderable groups. So if gamma is left orderable, then m is equal to 1 and n is equal to 1. So in the case when our matrix is actually just one number, one element of the group ring.
Rational version or?
Sorry? The integral one. So the integral. So from now on I will always talk about the integral because the rational one is settled. So then the integral is true. So it gives some hope, and I've been thinking of trying to generalize this to higher dimensions, right? To m and n arbitrary. And it turns out that what you need is the deep fall property to make it work. So, but first let's establish a translation between two languages, the language of matrices like this and the language of group actions that we talked about. So group action gamma on x hat, co-compact free as usual, corresponds to taking some matrix. So any group action and pick some, so fix some dimension I, and consider the boundary map as before. X hat ci x hat, the boundary map. As we just saw, this boundary map is given by some matrix. Then the boundary map di is equal to multiplication on the right by some matrix M for some M. For some matrix M. So once again, it's an M by N matrix with, yeah.
What do you mean by HX?
Fix some I. So I'm just taking some I, that's all. If you take a different I, you will get a different matrix. That's what I'm saying. But I'm only concentrating on just one of them. So you have a matrix. But conversely, given you cannot, maybe I shouldn't say conversely. Given a matrix, you can cook up actually a complex and a group action. But let's not do this. What I want to say is that whatever kind of argument you might come up with for group actions, you can do the same kind of argument for matrices. So in particular, the deep-fall property that we define for group actions, you can define the deep-fall property for a matrix. So that's what I mean by conversely. Given the matrix, we can do anything else, anything that we've done so far for group actions. So for any matrix M, we can define all the notions as before. So what are those notions? We assume that gamma is left orderable. So this matrix gives a map from m copies of L2 of gamma to n copies of L2 of gamma. But those m copies can be viewed as L2 of gamma cross some finite set 1 to m, 2 L2 gamma cross another finite set 1 to n. This matrix can be multiplication on the right by the matrix can be viewed as a map between these two. So we can consider just this set, and I can call it, given a matrix, I just need to pick a number. My I is going to be 0. So I think of this being the 0 dimension, and I'm thinking of this being the 1 dimension. So I is equal to 0 here, and I is equal to 1 here. But then you can just formally define sigma 0 corresponding to the matrix to be this gamma cross 1 to n. And then you can formally define sigma 1 just by definition gamma cross 1 to m. And then you get a map L2 of sigma 1 to L2 of sigma naught given by this matrix. So since we assume that gamma is left orderable, it gives an order. So there is an order on gamma which is invariant under the group. And we have some other set. Now we take the Cartesian product of these two. We can put an ordering on that set as well. So there is an ordering here, there is an ordering on this set, obviously. Then there exists a gamma invariant total order on sigma naught and on sigma 1. Total orders, maybe. Two different orders. And we can, this is exactly the same thing that we did before, right? We consider the set of I-dimensional cells. Now the sigma 1 and sigma naught are just defined formally from a matrix. But now you can apply exactly the same definitions as before. So you say, you consider sets like sigma 1 less than sigma, right? Given a, so what is sigma here? Sigma is an element of this. So sigma is here. Formally, it's a good idea to think of this being a cell, like in a cell complex. So we can consider all cells that are less than sigma. And then we can define the fall. The fall for, again, sigma in sigma 1 and some set in sigma 1, which is disjoint from sigma. How do you define the fall? You say sigma falls into this. Sigma falls into E if, as before, the boundary of sigma belongs to the closure of the space spanned by E. Follows. And then you say sigma is order essential.
Do we use boundary or what's the implication by it?
Yeah, I should say, yeah. Now I'm defining the boundary to be this. So there is you can use either model, right? So yeah, just define now. Define the boundary, yeah, to be the operation of multiplication on the right by m. And now exactly everything translates, right? If it falls if this happens, and then say sigma is order essential. If sigma falls into this set, sigma 1 less than sigma. And you say it's order inessential otherwise. Now we can state a claim. We can define the deep-fall property for matrices now. Before, the deep-fall property was a property of group actions. Given a group action, you can try to see if it satisfies the property or not. Now it becomes a property of matrices in exactly the same way. Given a matrix, you can ask, first of all, we need to define what it means, but you define it in exactly the same way. So what's the deep-fall property for the matrix? It means that if sigma falls, so for any sigma which is an element of this set sigma 1. So maybe I should say for any sigma in sigma 1. If sigma falls into the set of sigma 1, elements of sigma 1 that are less, then sigma falls into the set of inessential elements. Inessential, let's call them cells. So the elements of that sigma 1 I'm going to call cells. Exactly the same property, but now stated for matrices. Maybe I can call it 1 here. This is the deep-fall property for a matrix. And now we can, I claim that, so claim. If the deep-fall property, so the short way of saying is that the deep-fall property, deep-fall property for gamma. So there is a little discrepancy, right? The ATIA problem is a question about groups. So given a group, is it always true that for any matrix the dimension of the kernel is integral? The deep-fall property is not a property of groups. It's rather a property of group actions on complexes. Or it can be restated as a property of matrices over the group. So I need to be a little bit more specific here. But let me say it this way, briefly, that the deep-fall property implies the ATIA problem. That's a short way of saying this. So what does this actually mean? It means that if you have a matrix or a group action, either one, and you know that that matrix or that group action satisfies the default property, then for that particular action or for that particular matrix, if you take the kernel of that matrix, then the dimension of the kernel will be integral. So you see, philosophically, it suggests looking at the idea problem not as a question about groups, but rather as a question about group actions on complexes, or as a question about matrices. So philosophically, one should probably ask, given a group, for what actions of that group the corresponding kernel will have integral dimension, and for what actions it will not. It should be some kind of classification question rather than asking for what groups it always holds that the kernel is integral dimensional. So why does it hold? So we start with this map L2 sigma 1 to L2 sigma naught, and it's the operation of multiplication by m, which we denote d. We pretty much have the argument now. So what is sigma 1? Again, you consider the set of inessential cells, and then the complement of that is the set of essential cells, right? What's the definition of this I here? It's the set of all inessential ones, all those sigmas which do not satisfy this property, and the set of essential cells which do satisfy this property. Then it means that sigma 1 is split again into essential cells and the inessential cells. And then this boundary map L2 is split into essential plus the inessential part, and then the boundary, and then L2 of sigma naught. And instead of L2 of sigma naught, let me just consider the image of this map, the closure of the image. So the boundary of L2 of sigma 1, closure. Just by restricting the range, I guarantee that this is a weakly surjective map. Just by definition, because it's the closure of the image is the range. So weakly surjective. Then restrict this. We play the same game as before. We restrict this map to just order inessential cells. So I consider the same map, just restricted. L2 of sigma 1. What can we say about this map? Maybe I can. Let me just say order inessential here. So I just made this map weakly surjective as well, just by restricting the domain. So also weakly surjective. And let's go backwards. Start with this map, and then add all those essential cells to the domain. What happens? The default property says it means that since this is essential, so I pick some sigma in here, an essential cell, and now apply the default property. Since the cell is essential, it means that this holds. So this is equivalent to saying that the cell sigma is essential. If sigma is essential, then this holds. But that means that the boundary of sigma is is an element of the closure of the boundary of this. So for any sigma in essential cells, the boundary of sigma lies in the boundary of the closure of this. So the boundary of L2 of the inessential ones. So maybe I should say less than sigma, but in particular this is a subspace of the boundary of L2 of just inessential cells. But that means that if I just I pick some sigma here and I add this sigma to this domain, so increase the dimension just by 1. That sigma does not increase the closure of the image at all. The closure of, after adding this sigma to here, the closure of the image does not increase, does not change. And then of course I can take every single sigma and add all of them. And the closure of the image does not change. So then it implies that this range and this range are the same. L2 of sigma 1 is the same as the boundary of L2 of other inessential ones. They are the same. So what happened? We took some map and we increased the domain, but the result is that the image did not change. What can you say about then the kernel of this map and the kernel of this map? It means that everything that you added here contributed to the kernel. The dimension contributed to the kernel. But what is the kernel of this map? We did this. We already proved that the restricted boundary map, when you restrict it to only other inessential edges or cells in general, that map is injective. You pretty much use the definition of other inessential. Adding, you take one other inessential cell and consider all the ones that are smaller than that cell. Then adding that cell to that set increases the dimension, the usual dimension, exactly by 1. And we took orthogonal complements and there was a dimension argument there. Exactly the same argument as before shows that this is injective. So I should write here and injective. So this is an injective map. So the kernel of this map is 0. Now we added this much to the domain. And we added it in such a way so that the closure of the image did not change. But that means that what's the dimension of the kernel then? So this implies that the dimension let me write it here. The dimension over gamma of the kernel of the following map, of that map, original map, L2 of sigma 1 to L2 of sigma naught. So the dimension of the kernel of this map is the same as of course, it's the same kernel here. But the dimension of the kernel here is exactly how much you added to this space, just as with finite vector spaces, finite dimensional vector spaces. If you have one injective map and then you increase the domain of the injective linear map in such a way so that the image does not change, then it means that you increase the dimension exactly by how much you added to the domain. The kernel of this is the same as the kernel of this, which is the dimension. So we use additivity. It's the same as the dimension of L2 of E1. over gamma. What's important about this? Because this is an integer. Because this is, again, it's just several copies of L2 of gamma. The set here is split into orbits. Each orbit is a copy of gamma. So this is L2 of gamma to some finite power. But the dimension of that is an integral number. Is that finite power. Okay, it's an integer. Which pretty much which proves the Atiyah problem for this given matrix. So this gives a plan. A plan to address maybe the Atiyah problem. Try to find, at least in the case when groups are left orderable. In order to of course, one would hope to have a general argument, and that's what I was hoping to get, but I didn't quite get. And it looks like there might be some counterexamples. I don't see an easy argument for proving the Atiyah problem in general. So the plan is to try to find maybe many examples when the Atiyah problem holds. So but in order to find those examples, it suffices to find many examples of group actions for which the default property holds. So find many examples of group actions, of actions gamma on complexes X that satisfy the default property. This will imply that those examples satisfy the Atiyah problem. Of course, when I say default property, it means I'm already assuming that gamma is left orderable, because in the definition of default property we used left orderability. That's one. So I hope that's a good motivation for considering that that property. And the second motivation is submultiplicativity.
So does it already prove that free groups satisfy a problem for general matrices?
No, I don't know how to prove the default property for free groups. There should be an argument. I'm pretty sure there should be, but I don't have it. I can give an argument for Linnell's theorem in the case when M and N are 1. In general, I don't know the general argument. That's a very good question. Yeah. So that's the first motivation. And the second motivation is the submultiplicativity, which is a generalization of the Hanna-Neumann conjecture. The second claim is the default property property implies implies submultiplicativity. Again, it's a little imprecise. I need to make a more precise statement. It means that we consider the category of leakages over a given complex X. So X hat, we assume that there is a free co-compact group action on X hat. Consider the category of leakages over over X, and more precisely gamma leakages. So it's all maps all functions of this type. Y hat goes to X hat, and this map is supposed to be a leafage, and also Y hat should have a group action, and the action should commute with the map. In this category we have fiber product. So given any pair so you take one leafage in this category, one object in this category, this is another object in this category. You take the fiber product. This fiber product is also a leafage. This S hat is a leafage over X hat. So the fiber product of two objects is again an object in this category. And then you want to show the inequality. Again, you need to fix some dimension I. So fix some I. Some I. And in that particular dimension, you look at the A L2 number. AI. So under what conditions? Submultiplicativity question is asking under what conditions does this hold? And this is a partial answer to that. If your spaces, so namely what I need, if Y hat and Z hat satisfy the deep fall property for the given maps, then submultiplicativity holds. And why does it hold? Again, for the same reason. You take the I-dimensional cells of Y hat, and you split them into two parts: order essential cells and order inessential cells. Disjoint union with order inessential. Similarly for Z hat, and you check that if you restrict this map just to order inessential cells, then this map is injective. What is this A here? A is the dimension of the kernel. So if this is empty, if this set is empty here, then it means that the kernel is 0. But then you put it back. You add those essential I-dimensional cells. It means that you increase the dimension of the kernel from 0 to what? To the dimension of this, the dimension of the space generated by this. But that is an integral, right? So in particular, it's an integral. And then you take the fiber product. This S hat is a fiber product, and then check that so then check so similarly for S, maybe I should write the order essential cells for S hat. There is an injective map from this to the order essential cells of Y hat cross order essential cells of Z hat. You just use the definition of order essential. The definition of order essential says it's an analytic definition, right? Before we had a combinatorial version of it. We said that an edge for graphs, for example, right? An edge is order essential if there is a vein consisting of smaller edges. But now you state everything in purely analytic terms. A sigma is order essential, so let me write this again. It means that it belongs to the closure of the boundary of the smaller, say for Y hat I This is what it means to be order essential. The only thing that you need to check is that this property is preserved under this map and under this map. But this property, again, this property depends only on the component containing sigma. So this map is a leafage here. We have a component, several components, and then we have so x hat might be, for example, connected, but this doesn't have to be connected. This is y hat. And we have this sigma somewhere. This is sigma. Some cell in just one component. You check that this property here depends only on the component containing sigma. So instead of considering the whole y hat here, I could take just, so I could write this property. The same thing, but sigma I k less than sigma, where k is a component. K is the component of, the connected component of y hat, which contains sigma. So sigma belongs to k. If we took k to be the component containing sigma, then these two properties are equivalent. That requires a little bit of checking, but it's not hard to check. So this pretty much implies that if I have an order essential cell in S hat, then its image here and its image here also will be order essential. And but moreover, then, since we have a group action, I can remove those hats. So of S, more importantly, what we need is the quotient of this embeds into y hat without hat, z hat. So S is the quotient of S hat by the group action. So it's the set of orbits. This is the set of orbits in y hat, and this is the set of orbits in z hat. So you take this diagram and then you consider the quotient spaces of the quotient sets of those by the action of gamma. Exactly the same argument. So pretty much what we used in a proof of the Hahn-Neumann conjecture was leafages and ordering, and the fact that the deep fall property holds. So that's another motivation for this, and I'm pretty much finished. If you have any questions, please ask. Yeah.
Could you give us an example of any type of gamma module? Each dimension is rational.
Yeah, that was the homework, and I want to leave it for you to do. So, so the hint is that you consider groups with torsion. Right? Think about finite groups.
I think we didn't actually any general dimension for Hilbert gamma module. I don't think we actually exactly define dimension of Hilbert gamma module.
I did define it. Yeah. It's the sum. You pick a basis in the ambient space, and then you project each vector in a basis into the subspace, and then you take the square of the length. That was the definition. So it was the given, let's see, V subspace of L2 of gamma n. If you have an invariant subspace which is closed, then the dimension. So the dimension over gamma of V. So once again, I'm assuming that V is invariant under the group action. By definition, is the sum I goes from 1 to n. You take bi, and then the Cartesian, the dot product, the inner product with the projection V of bi. This is the same as the sum I goes from 1 to n of the length. This is the same as the dot product of this projection with itself. And that's the same as the length of the projection, bi squared. So this can be taken as the definition, where bi's are what? Like b1, you take the first copy of L2 of gamma. b1 represents that delta 1, the element corresponding to the identity element of the group. b2 corresponds to the identity element in the second copy, and so on. So those bi's are delta 1s for different copies of L2 of gamma here.
Then is it possible sub gamma module have a greater dimension than the original, the dimension of original total gamma module?
It's impossible, and it follows from additivity. If V is a subspace here, I can think of the inclusion map L2 gamma to the n. Consider this map. Now I can consider the image of this map and take the closure and take the quotient of L2 gamma n over the closure. So let's call it, I don't know, alpha, say. Then you take the image of alpha closure. Take the quotient. This goes to 0. This becomes a weakly short exact sequence. And then it means that the dimension of V plus the dimension of this, whatever it is, must be equal to the dimension of this. But this dimension, whatever it is, it cannot be negative. It's a non-negative number. So that means that the dimension of V, dimension over gamma of V, is at most the dimension of the ambient space, L2 of gamma n. Wait. So yeah, additivity implies this monotonicity. The dimension is monotone. Okay, do you have any other questions?
So when we discussed all these things, gamma is finitely presented because it's compact action.
First of all, I'm not assuming the complex. So if gamma acts on this y, I'm not assuming this y had to be simply connected at all. It doesn't have to be simply connected. That's the first thing.
Oh, I see. But you not simply connected. So, but you assuming that is a co-compact, right?
I'm assuming it's co-compact, but on some it might be very complicated complex.
Maybe it's just a disjoint union or lots of.
It could be a disjoint union. Yeah, you could take a copy of some complex for each element of gamma and just permute them. So this is gamma, and this is the complex. You pick something for each element of gamma, and gamma just permutes them. That's also allowed.
Okay. So Athia's problem is for not only for finitely generated, but also for all.
Not only for what?
Finitely generated work.
It's equivalent. If you know the Athia problem for any finitely generated group, then any group will satisfy that. Let's see. At least it's certainly true for zero divisors. It should be true for the Athia as well.
So it's like gamma. That gamma module you constructed this L2 module. You take a, let's say, finitely generated subgroup. Then
yeah, you should. That is true. That is true. The reason is that it's a question about a matrix.
Right.
But that matrix is finite, and each entry in the matrix is a finite linear combination of group elements. This M, you remember?
Once M is given, then you can restrict in this finite.
Exactly.
Right?
Given M, you restrict it to only finitely many elements, only finitely many elements of the group actually occur in this matrix. So you can consider the group generated by those finitely many elements, and everything restricts, yeah. Any other questions? Okay, I'm very happy to say that this is the end of the lecture. Thank you very much.